You are made of broken perfection. Right now, every atom in your body, every photon of light hitting your eyes, every gravitational tug holding you to the earth, all of it exists because the universe suffered a flaw. Not a catastrophe, not an error, something far stranger. A perfection so unstable that it couldn't hold, and when it fell apart unevenly. And from that uneven collapse came everything. Here is a number that should keep you awake tonight: the bare mass of the 3 quarks inside a proton. The particles that account for virtually all the weight of every atom in your body adds up to roughly 9.5 megaelectronvolts, but a proton weighs 938 megaelectronvolts. That means more than 99% of the mass of everything you have ever touched, everything you have ever held, every mountain and ocean and star and grain of sand did not come from the particles themselves. It came from the breaking of a symmetry. The actual stuff inside matters is almost weightless. Your mass is a ghost of a transformation that happened when the universe was younger than a heartbeat, and it gets stranger if that symmetry had broken perfectly, if the flaw had been clean, and even there would be no matter at all. Not a single atom, not a single star. For every particle of matter the Big Bang created, it also created a matching particle of antimatter. And antimatter is the mirror twin of matter. When they meet, they annihilate one another and vanish into pure energy. If the breaking had been flawless, every particle would have found its twin, and the entire cosmos would be nothing but a bath of cooling radiation. No galaxies, no chemistry, no life, no you. But the breaking was not flawless. It was imperfect by the slimmest conceivable margin. For roughly every billion particles of antimatter, there were 1,000,000,001 particles of matter. One extra survivor for every billion pairs that canceled. That tiny asymmetry, that 1 in a billion remainder, is the material content of the entire observable universe. You exist because symmetry broke, and you exist because it broke badly. This is the story of that breaking. It is a story that stretches from the first trillionth of a second after the Big Bang to the interior of the largest machine ever built by human hands. It involves a field that fills every point in the universe. A Japanese physicist who found inspiration in the theory of superconductors. A Scottish theorist whose paper was initially rejected by a journal. A Chinese-American experimentalist who proved that the universe distinguishes left from right. And 2 physicists who accidentally discovered that even the symmetry between matter and antimatter is not sacred. It is also, possibly, a story that has not yet ended. Because the breaking that gave us mass and matter may itself be temporary. The universe may be sitting in a state that is not its lowest possible energy, balanced on a ledge above a deeper valley. And if it ever falls, everything we know will be rewritten at the speed of light. But we will get to that. First, we need to understand what symmetry means to a physicist and why breaking it is the most creative act in all of nature. Symmetry in everyday life is a familiar idea. A butterfly's wings mirror each other across its body. A snowflake looks the same when you rotate it by 60 degrees. A sphere looks identical from every angle. These are all examples of geometric symmetry, and they carry a certain aesthetic appeal. Humans have been drawn to symmetry for thousands of years, from the columns of ancient Greek temples to the repeating geometric patterns of Islamic tile work to the soaring arches of Gothic cathedrals. There is something in the human mind that responds to balance, to regularity, to the sense that the world has order. But in physics, symmetry means something deeper and far more powerful. In physics, a symmetry is not about how things look, it is about how things behave. A symmetry exists whenever you can change something about a system, perform some transformation, and the fundamental laws governing that system remain unchanged. If you move your experiment from one side of a laboratory to the other, the laws of physics do not change. That is translational symmetry. If you rotate your apparatus to face a different direction, the results come out the same. That is rotational symmetry. If you run your experiment today or tomorrow, assuming identical conditions, you get the same result. That is time translation symmetry. If you replace every particle with its corresponding antiparticle, certain laws remain unchanged. That is charge conjugation symmetry. If you reflect the spatial coordinates, swapping left for right, certain processes appear identical. That is parity symmetry. These might sound like trivial observations. They are anything but. In 1918, a German mathematician named Emmy Noether proved one of the most beautiful theorems in all of science. Noether was working at the University of Göttingen at a time when women were not allowed to hold official academic positions. She lectured under the name of her colleague, David Hilbert, and for years, her work went formally unrecognized by the institution. Yet her theorem, proved when she was 36 years old, would become one of the cornerstones of modern physics. Noether demonstrated that every continuous symmetry of a physical system corresponds to a conserved quantity. Translational symmetry gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum. Time translation symmetry gives you conservation of energy. These are not separate facts you have to memorize. They flow from a single insight. Symmetry and conservation are two faces of the same idea. The reason energy is conserved is that the laws of physics do not change over time. The reason momentum is conserved is that the laws of physics are the same everywhere in space. These are not coincidences. They are mathematical necessities. Noether's theorem lies at the foundation of modern physics. Every equation a physicist writes down, every model of reality they build, begins with the symmetries they believe the universe obeys. the standard model of particle physics, the most successful theory of nature ever devised, is constructed entirely from symmetry principles. It describes a universe governed by gauge symmetries, mathematical structures so abstract that they defy easy visualization, but so powerful that they predict the existence of particles, forces, and interactions with extraordinary precision. The standard model predicted the existence of the W and Z bosons before they were discovered, predicted the existence of the top quark before it was found, and predicted the existence of the Higgs boson nearly half a century before it was confirmed at CERN. So if symmetry is so fundamental, so pervasive, so constitutive of how the universe works, then an obvious question arises. The universe we actually observe is not symmetric. Particles have different masses, forces have different strengths and ranges. Matter dominates over antimatter. The electromagnetic force reaches across the cosmos, while the weak force barely extends beyond the radius of an atomic nucleus. Left-handed particles behave differently from right-handed ones under the weak force. If the laws are symmetric, why is the world so plainly asymmetric? Consider what a truly symmetric universe would look like if the electroweak symmetry had never broken. The W and Z bosons would be massless, just like the photon. The weak force would have infinite range, identical to electromagnetism. There would be no distinction between these two forces at all. They would be a single unified electroweak interaction carried by four massless bosons. The electron would be massless. The quarks would be massless. Every particle in the standard model would travel at the speed of light, unable to slow down, unable to be captured, unable to bind into atoms or molecules or anything resembling structure. There would be no atoms, no chemistry, no stars, because stars require gravity to compress matter that first must be able to clump together, which requires mass. A universe with perfect electroweak symmetry would be a featureless plasma of massless particles streaming past one another at light speed for eternity. It would be, by any human standard, empty. Not because it lacked particles, but because those particles could never form anything. The physicist Chris Quigg of Fermilab once spent considerable effort thinking about what such a world would actually look like. Even without the Higgs mechanism, QCD would still confine quarks, and the strong force would still generate a condensate. Baryons would still form, but with very different properties. The pions, now truly massless Goldstone bosons, would become lighter than the electron, and the entire landscape of nuclear physics would be unrecognizable. There might be some form of matter held together by the strong force, but it would bear no resemblance to the periodic table of elements we know. Chemistry, as we understand it, would be impossible. Biology would be inconceivable. So the question is not academic. It is not a puzzle for mathematicians to contemplate in the abstract the difference between a symmetric universe and a broken one is the difference between a sterile void and the rich, structured cosmos we inhabit. Understanding how symmetry breaks is understanding why anything exists at all. The answer is one of the most profound ideas in all of physics. The laws can be symmetric even when the outcomes are not. Imagine a pencil balanced perfectly on its tip. The physical setup is symmetric. Gravity pulls straight down, and there is no preferred direction for the pencil to fall. Every direction is equally likely. The pencil, in its balanced state, respects the rotational symmetry of the forces acting on it, but that state is unstable. The slightest perturbation, a vibration in the table, a stray air current, even quantum fluctuations at the atomic level will cause the pencil to tip, and when it tips, it has to fall in some specific direction. The symmetry that existed before is now hidden. The pencil on the table points in one particular direction, even though nothing in the underlying physics preferred that direction. The laws are still symmetric, but the state of the system is not. This is spontaneous symmetry breaking. The word spontaneous is crucial. Nobody pushed the pencil. No external agent chose the direction. The system broke its own symmetry simply by settling into its lowest energy state. The symmetry is still there, encoded in the equations. It simply is not manifest in the particular state the system occupies. It is hidden, not destroyed. Now imagine something more revealing. Picture the bottom of a wine bottle or the brim of a wide-brimmed hat, the shape physicists call the Mexican hat potential. In the center, at the very top, there is a peak. All around the peak, sloping downward, there is a circular trough, a valley that forms a ring. If you place a marble at the very top of the peak, the system is perfectly symmetric. From the marble's perspective, every direction looks the same. There is no preferred direction on the rim of the hat. But the peak is a point of maximum energy, not minimum. It is unstable. The marble will roll off the peak and settle into the trough somewhere along the ring. Where it settles is arbitrary. Nothing about the shape of the hat prefers one point on the ring over another. But the marble must settle somewhere, and wherever it lands, the symmetry is broken. The marble now occupies a definite position on the ring, even though the ring itself remains perfectly symmetric. This image is not just a helpful analogy. It is, in simplified form, the exact mathematical structure of the field that gives particles their mass. And the moment that marble rolls off the peak and into the valley is the moment the universe, as we know it, began to take shape. This kind of transition happens throughout nature, not just in the abstract mathematics of particle physics. Consider a lump of iron heated above 770 degrees Celsius. Its Curie temperature. At that temperature, the thermal energy is so intense that the tiny magnetic domains within the iron, each containing billions of atoms with their own magnetic orientations, point in random directions. On average, they cancel each other out. The iron has no net magnetization. It is magnetically symmetric. No preferred direction. If you rotate the entire block, it looks the same. But as the iron cools below the Curie temperature, something remarkable happens. The thermal fluctuations diminish, and the interactions between neighboring atomic magnets become strong enough to overwhelm the randomizing effect of heat. The atomic magnets begin to align. They lock into a common direction, and the iron becomes a permanent magnet. It now has a definite North Pole and a definite South Pole. The underlying physics, the equations governing the interactions between atoms, never changed. They are still rotationally symmetric. But the state of the system is not. The magnet points in a particular direction. Symmetry has been spontaneously broken. Ice forming in water follows a similar pattern. Liquid water is isotropic. It looks the same in every direction at every point. But when the temperature drops below 0 degrees Celsius, the water molecules lock into a crystalline lattice with very specific spatial orientations. The full rotational and translational symmetry of the liquid phase is reduced to the much more limited symmetry of the ice crystal. Hexagonal ice has a 6-fold rotational symmetry, which is far less than the continuous rotational symmetry of the liquid. The laws governing molecular interactions have not changed. But the ground state of the system, the configuration with the least energy, has less symmetry than the laws themselves. The universe, it turns out, has undergone precisely this kind of transformation. Not once, but several times in the first fractions of a second after the Big Bang, and the physicist who first recognized how to apply this idea to the world of subatomic particles was a quiet, brilliant Japanese-American theorist named Yoichiro Nambu. Nambu was born in Tokyo in 1921 and grew up during what would later be recognized as a golden age of Japanese physics. Heideki Yukawa, who predicted the existence of the meson, had received Japan's first Nobel Prize in 1949. Shinichiro Tominaga would share the 1965 Nobel Prize for his work on quantum electrodynamics. The intellectual atmosphere was vibrant, and Nambu absorbed it deeply. He graduated from the University of Tokyo in 1942, in the middle of World War II. Like many physicists of his generation, he spent the war years working on military applications of radar. After the war, he joined a select group of theoretical physicists at the newly formed physics department at Osaka City University. He spent 3 formative years there, and later recalled them as a time when he had never felt and enjoyed so much the sense of freedom. By 1952, he had completed his doctorate at the University of Tokyo, and after a brief stint at the Institute for Advanced Study at Princeton, he arrived at the University of Chicago in 1954, where he would spend the rest of his career. His colleagues described him as extraordinarily quiet, almost shy, but possessed of an intellect so deep that his ideas routinely anticipated developments that would take the wider physics community years or even decades to appreciate. Frank Wilczek, who won his own Nobel Prize for work on the strong force, said of Nambu that his work was an act of imagination that was way ahead of its time. Peter Higgs, whose own Nobel-winning mechanism was directly inspired by Nambu's work, acknowledged in interviews that Nambu was the one who showed how fermion masses could arise from spontaneous symmetry breaking. In the late 1950s, Nambu was studying the theory of superconductivity, the bizarre phenomenon in which certain metals, when cooled to extremely low temperatures, lose all electrical resistance. In 1957, John Bardeen, Leon Cooper, and Robert Schrieffer published their BCS theory, explaining how electrons in a superconductor pair up, forming so-called Cooper pairs, and collectively break the electromagnetic gauge symmetry within the material. The Russian physicist Nikolai Bogoliubov had developed a mathematical formalism for describing these pairs using a particular kind of transformation. And Nambu noticed something remarkable. The Bogoliubov equations bore a striking resemblance to the Dirac equation, the fundamental equation governing the behavior of fermions like electrons and quarks. This was not a casual observation. It was the kind of insight that changes the course of a field. Nambu made an intellectual leap that connected two seemingly unrelated areas of physics. He took the concept of spontaneous symmetry breaking from superconductivity and applied it directly to the world of elementary particles in 1960 and 1961, working with the Italian physicist Giovanni Gionalasinio, then a research associate at Chicago. He published two seminal papers proposing a model, now known as the Nambu-Gionalasinio model, in which particles could acquire mass not because they were born with it, but because a symmetry was spontaneously broken by the vacuum of the universe itself. In their model, massless fermions interacting with each other through a particular kind of coupling would, below a certain energy scale, develop mass. The vacuum state of the theory was not symmetric under a transformation called chiral symmetry, even though the fundamental equations were. Chiral symmetry involves the independent transformation of left-handed and right-handed components of a particle. In a chirally symmetric theory, left-handed and right-handed particles are treated identically, but in the NJL model, the vacuum spontaneously chose a state that distinguished between them, and this distinction gave the fermions mass. This was revolutionary in the deepest sense. It meant that the mass of a particle was not a fixed property written into the laws of nature at the most fundamental level. It was an emergent property, arising from the way the vacuum chose to organize itself. The vacuum, the emptiest possible state of space, was not empty at all. It had structure. It had properties. And those properties could break symmetries and generate mass. As Wilczek would later put it, Nambu introduced the idea that what we perceive as empty space is, to a deeper vision, a medium that complicates the motion of matter we observe. Nambu's work also predicted something else, something equally important. A mathematical theorem, eventually formalized as the Goldstone theorem, after Jeffrey Goldstone proved a rigorous version of it in 1961, states that when a continuous symmetry is spontaneously broken, new massless particles must appear in the theory. These are now called Nambu-Goldstone bosons. Nambu realized that the pions, the lightest strongly interacting particles, were approximately these Goldstone bosons. They were not exactly massless because the underlying chiral symmetry was not perfectly spontaneous. The small but non-zero masses of the up and down quarks explicitly break the chiral symmetry slightly, giving the pions a small mass, but the pions are dramatically lighter than other hadrons, about 7 times lighter than a proton. And this anomalous lightness was a smoking gun for spontaneous symmetry breaking. Nambu received half of the 2008 Nobel Prize in Physics for this discovery. The other half was shared by Makoto Kobayashi and Toshihide Masukawa for work on a different kind of symmetry breaking, one involving the symmetry between matter and antimatter, which we will encounter later in his Nobel acceptance speech, which was delivered on his behalf by Jonah Lacinio because Nambu's health prevented him from traveling to Stockholm. The quiet genius reflected on his life's work with characteristic modesty. He said that the principle of spontaneous symmetry breaking explains why the world is so complex. In spite of the many symmetry properties in the basic laws that are supposed to govern it, the basic laws are very simple. Yet this world is not boring. That, he concluded, is an ideal combination. Nambu died in Osaka on July 5, 2015, at the age of 94. His contributions to physics were so numerous and so far-reaching that colleagues said he could have won the Nobel Prize for any of several different pieces of work. In addition to spontaneous symmetry breaking, he was a pioneer of quantum chromodynamics and one of the founders of string theory. But it was his insight that the vacuum of the universe has the power to break symmetries and generate mass that reshaped our understanding of why anything has weight, why the forces of nature are different from one another, and ultimately why matter exists at all. But Nambu's symmetry breaking, powerful as it was, concerned the strong force and the masses of composite particles like protons and neutrons. The question of why fundamental particles, the quarks, electrons, and neutrinos themselves, have mass required a different mechanism, one that operates in the electroweak sector rather than the strong sector, and the answer would come from a field that fills every point in the universe, proposed on paper by 3 independent groups in 1964, and confirmed in a laboratory 48 years later. In the early 1960s, theoretical physicists were struggling with a fundamental problem threatened to undermine the entire framework of gauge theories. They had made extraordinary progress in understanding the electromagnetic and weak nuclear forces. The electromagnetic force, carried by massless photons, is responsible for light, chemistry, magnetism, and virtually all everyday phenomena. The weak force is responsible for certain kinds of radioactive decay, including the beta decay that powers part of the sun's energy production. Sheldon Glashow, Abdus Salam, and Steven Weinberg were developing a theory that unified these two forces into a single electroweak interaction, arguing that at sufficiently high energies, they were indistinguishable. The mathematics was elegant. The symmetry group was clean. But the theory had a fatal, seemingly inescapable problem. The mathematics of gauge symmetry, the kind of symmetry that governs force-carrying particles called gauge bosons, demanded that these bosons be massless. This is a strict mathematical requirement, not a suggestion. If you write down a mass term for a gauge boson in a gauge invariant Lagrangian, the term violates the gauge symmetry, and the theory becomes mathematically inconsistent. It produces infinities that cannot be renormalized, predictions that are nonsensical. The photon, the carrier of the electromagnetic force, is indeed massless, so that posed no problem. But the carriers of the weak force, the W+, W-, and Z bosons, had to be massive. Even before their direct discovery, physicists knew this from the short range of the weak force. A force carried by a massive particle has a limited range, inversely proportional to the carrier's mass. The weak force barely extends beyond the diameter of an atomic nucleus, implying that its carriers must be very heavy. When the W and Z bosons were finally discovered at CERN in 1983, their masses were measured at roughly 80 and 91 gigaelectronvolts, respectively, about 80 to 90 times the mass of a proton. This was the impasse. Gauge symmetry demanded massless force carriers. Nature demanded massive ones. If you insisted on the symmetry that made the theory consistent, you could not have mass. If you simply inserted mass by hand, the theory fell apart. Something had to give. The situation was not merely frustrating. It was existentially threatening to the entire program of understanding forces through gauge theories. Yang-Mills theories, the general class of gauge theories named after Chen-Ning Yang and Robert Mills, who had proposed them in 1954, were mathematically beautiful and clearly relevant to nature, but without a way to give gauge bosons mass while preserving the mathematical consistency of the gauge symmetry. They seemed useless for describing the weak force. Some physicists began to wonder whether the gauge theory approach was simply wrong for the weak interaction. Others hoped for a clever mathematical trick that could reconcile the irreconcilable. The trick, when it came, was not a trick at all. It was a deep physical insight into the nature of the vacuum. In 1964, 3 independent groups of physicists proposed a solution almost simultaneously. Robert Brout and Francois Englert published their first paper in Brussels on August 31. Peter Higgs in Edinburgh published shortly after, on October 19, having added a crucial sentence to his revised paper, noting that the mechanism implied the existence of a new massive scalar particle. Gerald Guralnick, Carl Hagen, and Tom Kibble published in London in November, providing the most complete treatment of the mathematical details. All three groups arrived at essentially the same idea, now collectively known as the Brout-Englert-Higgs mechanism, or more commonly, the Higgs mechanism. The idea was built directly on Nambu's concept of spontaneous symmetry breaking, and on earlier work by Philip Anderson, who had proposed a similar mechanism in the context of condensed matter physics in 1962. Anderson had shown that in a superconductor, the photon effectively acquires a mass inside the material, a phenomenon directly related to the Meissner effect, the expulsion of magnetic fields from a superconductor. Anderson suggested that this mechanism could be generalized to relativistic theories, but he did not construct an explicit relativistic model. That final step was taken by Brout, Englert, Higgs, Guralnick, Hagen, and Kibble. It would take several more years before Steven Weinberg and Abdus Salam, working independently, incorporated the Higgs mechanism into a complete theory of the electroweak interaction. In 1967, Weinberg published a paper applying the mechanism to the Glashow model of unified electroweak forces, producing specific predictions for the masses of the W and Z bosons and the existence of neutral current interactions. Salam arrived at an equivalent formulation independently. Their electroweak theory, combined with the Higgs mechanism, was eventually shown to be renormalizable by Gerard 't Hooft and Martinus Veltman in 1971, meaning that the infinities in the calculations could be systematically removed, making the theory predictive. This proof of renormalizability was the turning point. It convinced the physics community that the electroweak theory was not just an elegant idea, but a rigorous, testable, calculable theory of nature. 't Hooft and Veltman received the 1999 Nobel Prize for this work, and Glashow, Weinberg, and Salam shared the 1979 Nobel Prize for the electroweak unification itself. The core idea of the Higgs mechanism was breathtaking in its audacity. Imagine a new scalar field pervading all of space. Unlike other fields, this one has a peculiar property. Its potential energy is shaped like the Mexican hat we described earlier, with a central peak and a circular valley. At extremely high energies, the kind of energies that existed in the first moments after the Big Bang, the field sits at the peak of the hat. The full electroweak symmetry is unbroken. All force carriers are massless. Electromagnetism and the weak force are indistinguishable. Everything is symmetric and, in a certain sense, featureless and uniform. But as the universe expands and cools, this symmetric state becomes unstable. The field, like the marble on the peak of the hat, rolls down into the circular valley. It acquires a non-zero value everywhere in space, a constant background value that physicists call the vacuum expectation value. This value is approximately 246 gigaelectronvolts. It is not zero. The field is always on, everywhere, right now, in the room where you are reading or listening to this. You are immersed in it. Every particle in your body is interacting with it at this very moment. When the field settles into the trough, the electroweak symmetry breaks spontaneously. The Higgs field has 4 mathematical components, 4 degrees of freedom. 3 of these are absorbed by the W+, W-, and Z bosons, giving them mass and transforming them from massless, long-range force carriers into massive, short-range ones. These 3 absorbed components become the longitudinal polarization states of the massive gauge bosons, providing them with the additional degree of freedom that a massive particle possesses, but a massless one does not. The 4th degree of freedom becomes a new particle, a quantum excitation of the settled field, a ripple in the background. That particle is the Higgs boson. The photon, meanwhile, remains massless. This is because the symmetry breaking is not total. One particular combination of the original gauge symmetries survives intact, corresponding to the unbroken electromagnetic gauge symmetry. The photon is the force carrier of this surviving symmetry. This is why electromagnetism has an infinite range, while the weak force barely extends beyond the diameter of an atomic nucleus. They started as the same force, governed by the same symmetry. They became different forces because the symmetry broke unevenly, leaving one carrier massless and the others massive. The matter particles, the fermions like quarks and electrons, also gain their fundamental masses through interaction with the Higgs field, but through a different mathematical mechanism called Yukawa coupling. Each fermion species couples to the Higgs field with its own characteristic strength. The stronger the coupling, the more mass the particle acquires when the Higgs field settles into its non-zero vacuum value. The top quark couples very strongly and is extraordinarily heavy, about 173 gigaelectronvolts, making it the heaviest known elementary particle. The electron couples very weakly and is correspondingly light, about half a megaelectronvolt. The difference in mass between an electron and a top quark, a factor of more than 300,000, reflects the enormous range of Yukawa coupling strengths. The standard model does not explain why these couplings have the values they do. It treats them as free parameters that must be measured experimentally and entered into the theory by hand. Why the electron is so light and the top quark so heavy remains one of the great unsolved puzzles of particle physics. The universe underwent this electroweak phase transition roughly 1/1,000,000,000 of a second after the Big Bang, when its temperature dropped below about 160 gigaelectronvolts, or approximately 2 quadrillion degrees. To put this timescale in perspective, 1/1,000,000,000 of a second is to 1 second what 1 second is to approximately 32,000 years. The transition happened in the blink of an eye, at a time so early that the universe was smaller than a grapefruit and denser than the core of a neutron star. Before that moment, the electroweak symmetry was intact. All particles in the standard model were massless, racing around at the speed of light in a blisteringly hot, perfectly symmetric plasma of quarks, leptons, and gauge bosons. There was no distinction between the electromagnetic force and the weak force. The W and Z bosons were as massless as the photon. Electrons were as fast as light. The universe in this epoch was simpler and more symmetric than at any time since. If you could have taken a snapshot of any small region, it would have looked identical to any other region. No structures, no hierarchies, no preferred directions or scales. And then the Higgs field, which had been sitting at a value of 0 in the symmetric state, began to shift. The exact nature of this transition in our universe is still a matter of active research. Lattice QCD studies suggest that within the minimal standard model, the transition was not a sharp phase transition at all, but a smooth crossover, a gradual change without the dramatic bubble nucleation that characterizes a first-order transition. The Higgs field smoothly evolved from 0 to its current value over a temperature range of about 5 gigaelectronvolts, centered around 160 gigaelectronvolts. There was no sudden snap, no moment of discontinuity. Instead, the field crept into its new value as the universe cooled, and the properties of particles changed continuously along with it. However it occurred, the consequences were revolutionary. After that moment, the Higgs field settled into its non-zero vacuum state. The symmetry broke, and mass was born. The W and Z bosons became heavy and sluggish, each acquiring a mass about 80 to 90 times that of a proton. Quarks and electrons acquired their fundamental masses, different for each species, determined by the strength of their individual coupling to the Higgs field. The electromagnetic and weak forces diverged into the distinct phenomena we observe today. The photon remained massless, a reminder of the one surviving piece of the original electroweak symmetry. The universe, in that trillionth of a second, went from simple and symmetric to complex and differentiated. It was, in a very real sense, the moment the universe grew up. Peter Higgs himself was a quiet and self-deprecating Scotsman who spent most of his career at the University of Edinburgh. He had written his landmark paper in 1964, and it was initially rejected by the journal Physics Letters. The editor felt the paper had no obvious physical implications. Higgs revised it, added a single sentence at the end, noting that the theory implied the existence of a new massive scalar boson, and resubmitted it to physical review letters, where it was accepted. It was a brief paper, barely 2 pages, but its implications were among the most profound in the history of science. Higgs expressed frustration at the nickname God particle, coined by Leon Letterman for his book title, noting that Letterman had originally intended a less reverent term, but that the publisher had overruled him. Higgs turned down a knighthood in 1999. He died in Edinburgh on April 8, 2024, at the age of 94. For nearly half a century, the Higgs boson remained theoretical. Physicists knew it had to exist if the standard model was correct, but producing it required extraordinary energies and the most sensitive detectors ever built. The machine that finally found it sits beneath the countryside near Geneva, Switzerland, straddling the border with France. The Large Hadron Collider is a ring of superconducting magnets 27 kilometers in circumference, cooled to temperatures colder than outer space, about 1.9 kelvins, through which protons are accelerated to 100% of the speed of light before being smashed together inside massive detectors. 4 of these detectors are positioned at points around the ring. 2 of them, Atlas and CMS, are general-purpose experiments designed specifically to search for new particles, including the Higgs boson. By the end of 2011, both Atlas and CMS were seeing tantalizing hints. There appeared to be an excess of events around a mass of 125 gigaelectronvolts, exactly where the standard model predicted the Higgs boson should appear, but the statistical significance was not yet high enough to claim a discovery. In particle physics, the threshold for discovery is a statistical significance of 5 sigma, meaning there is less than a 1 in 3.5 million chance that the observed signal is a random fluctuation. The data collected through 2011 fell short of this threshold. In April 2012, the LHC restarted at a slightly higher collision energy, 8 teraelectronvolts instead of 7. Data poured in rapidly. By late June, the experimentalists knew what they had found, but the results were embargoed until the official announcement. Rumors leaked onto social media, amplified by the observation that Peter Higgs himself had been invited to attend the seminar at CERN on July 4. That morning, in a packed auditorium at CERN, Joe Incandela of CMS and Fabiola Gennady of Atlas presented their updated results to a live audience that included several of the surviving theorists who had predicted the particle. Peter Higgs was there. Francois Englert was there. Thousands of physicists around the world watched the webcast in the middle of the night. The data were unambiguous. Both experiments had independently observed a new particle with a mass of approximately 100 and 25 gigaelectronvolts. It had no spin. It had no electric charge. Its decay patterns were consistent with the Higgs boson predicted by the Standard Model. When CERN's Director General Rolf Ewer declared to the audience that from a layman's perspective they had found it, the auditorium erupted in sustained applause. Peter Higgs, then 83 years old, wiped tears from his eyes. He later said he had never expected to see the discovery in his lifetime. The following year, Higgs and Englert were awarded the Nobel Prize in Physics. Brout, who had been Englert's collaborator and co-author of the first paper, had died in 2011 and could not share the honor. The Nobel Committee cited their work on the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, confirmed by the discovery at the LHC. The discovery was more than the completion of a theoretical puzzle. It was the first direct evidence that an invisible field filling every cubic centimeter of the cosmos was responsible for giving particles the property that makes atoms possible, that makes chemistry possible, that makes you possible. In the years since the discovery, physicists have subjected the Higgs boson to increasingly precise scrutiny, measuring its properties with growing accuracy. They confirmed that it has zero spin, making it the only known fundamental particle with this characteristic. They measured its couplings to other particles and found them consistent with Standard Model predictions, confirming that heavier particles interact more strongly with the Higgs field. In 2016, the ATLAS and CMS experiments observed the Higgs boson's interaction with tau leptons. In 2018, they confirmed its interaction with top and bottom quarks. Each measurement tightened the case that this was indeed the Higgs boson of the Standard Model, and not some impostor from a more exotic theory. But questions remain. Is this the only Higgs boson, or are there more? Some theoretical frameworks, including supersymmetry, predict the existence of multiple Higgs particles, perhaps 5 or more, with different masses and properties. The LHC has found no evidence for additional Higgs bosons so far, but the search continues. Another critical question involves the Higgs boson's self-interaction, the way it couples to itself. This self-coupling determines the exact shape of the Mexican hat potential and is one of the key predictions of the Standard Model that has not yet been measured directly. Measuring it requires observing events in which 2 Higgs bosons are produced simultaneously, an extraordinarily rare process. The high-luminosity LHC, expected to collect data through the 2030s, should provide enough collisions to make this measurement, potentially revealing whether the Higgs potential has the precise shape the Standard Model predicts, or whether it deviates in ways that point to new physics. There is something almost miraculous about the Higgs discovery when you step back and appreciate its full scope. A field was proposed in 1964 on purely theoretical grounds to solve solve a mathematical inconsistency in the theory of the weak force. Its existence was inferred from indirect evidence for decades. And then, using a machine that took 30 years to design and build, buried 100 meters underground, accelerating particles to within a hair's breadth of the speed of light, physicists confirmed that this invisible, all-pervading field is real. It fills the room where you sit. It fills the space between stars. It fills the emptiest voids in the observable universe. And without it, you would not exist. But here is where the story takes an unexpected turn, one that takes us back to Nambu and the strong force. The Higgs mechanism gives quarks and electrons their fundamental mass, the mass written into the standard model equations. For the electron, that is essentially all the mass it has. But for the proton, the particle that constitutes the nucleus of every hydrogen atom in the universe, the Higgs-derived mass is almost irrelevant. The up quark has a mass of roughly 2.3 megaelectronvolts. The down quark weighs about 4.8 megaelectronvolts. A proton contains 2 up quarks and 1 down quark. So the total quark mass inside a proton is about 9.4 megaelectronvolts, but a proton weighs 938 megaelectronvolts. The quarks contribute roughly 1% of the proton's mass. The remaining 99% comes from somewhere else entirely. It comes from a second, independent act of symmetry breaking, operating not in the electroweak sector, but in the domain of the strong nuclear force. This is chiral symmetry breaking in quantum chromodynamics. QCD, the theory of the strong force, describes how quarks interact through the exchange of particles called gluons. Gluons carry what physicists call color charge, a quantum property analogous to electric charge. But with 3 varieties instead of 1, the strong force is extraordinary in its intensity. At short distances, inside a proton or neutron, it is so powerful that quarks are permanently confined. You can never isolate a single quark. If you try to pull 2 quarks apart, the energy stored in the gluon field between them becomes large enough to create a new quark-antiquark pair from the vacuum. And you end up with 2 bound states instead of 1 free quark. This is called color confinement, and it is one of the defining features of the strong force. Now, the equations of QCD have a particular symmetry when the quarks are massless. This symmetry is called chiral symmetry, and it involves independent transformations of the left-handed and right-handed components of the quark fields. In a chirally symmetric world, left-handed quarks and right-handed quarks behave identically under the strong force, and they can be rotated independently without changing the physics. But in the real vacuum of QCD, this symmetry is spontaneously broken. The strong force is so intense at low energies that it generates what is called a quark condensate, a non-zero average value of quark-antiquark pairs filling the vacuum. Think of it as a kind of invisible fog pervading all of space, composed not of water droplets, but of virtual quark-antiquark pairs bound together by the strong force. This condensate serves as the order parameter for chiral symmetry breaking, much as the magnetization of a ferromagnet serves as the order parameter for the breaking of rotational symmetry. The condensate distinguishes between left-handed and right-handed quarks, even though the fundamental QCD equations do not. When quarks interact with this condensate, they acquire what physicists call constituent masses. The bare-up quark, which weighs about 2.3 megaelectronvolts, according to the Higgs mechanism, is dressed by its interactions with the chiral condensate and the surrounding swarm of gluons, puffing up to an effective mass of roughly 300 megaelectronvolts. The same happens to the down quark. A proton containing 3 such constituent quarks, plus a roiling sea of gluons and virtual quark-antiquark pairs, ends up weighing about 938 megaelectronvolts. This is one of the most remarkable facts in all of physics. Virtually all the mass of ordinary matter does not come from the Higgs field. It comes from the energy of the strong force, locked inside protons and neutrons by the spontaneous breaking of chiral symmetry. Einstein's famous equation relating mass and energy, the one everyone recognizes, is made literal here in the most dramatic way possible. The mass of a proton is almost entirely the binding energy of the quarks and gluons inside it, converted into mass by the unyielding arithmetic of the strong force. Every time you step on a scale, 99% of the number you see reflects this energy. This might sound abstract, but consider what it means concretely. If you weigh 70 kilograms, about 69.3 kilograms of that comes from the energy of the strong force, from gluons zipping around inside your protons and neutrons at nearly the speed of light, from virtual quark-antiquark pairs popping into and out of existence billions of times per second, from the relentless churning of the QCD vacuum inside every single atomic nucleus in your body. Only about 700 grams of your weight, less than a kilogram, comes from the Higgs mechanism, giving your quarks and electrons their bare masses. The rest is pure energy, trapped by confinement, made manifest as mass. The interior of a proton is one of the most violent environments in nature. Far from being a simple collection of 3 quarks sitting quietly, a proton is a seething storm of activity at any given instant. It contains not just the 3 valence quarks, 2 up and 1 down, that give it its identity, but also a constantly fluctuating sea of gluons and virtual quark-antiquark pairs. Physicists who study the proton through deep inelastic scattering experiments, firing high-energy electrons at protons and analyzing the debris, have found that gluons carry roughly half the proton's total momentum. The quarks carry the other half. The proton's mass is not located in any one particle inside it. It is distributed across the entire system, emerging from the collective dynamics of quarks and gluons, interacting through the spontaneously broken chiral vacuum of QCD. Understanding this mechanism quantitatively has been one of the great triumphs of computational physics. Lattice QCD calculations, performed on some of the world's most powerful supercomputers, have confirmed that the proton mass can be calculated from first principles using only the fundamental parameters of QCD, the strong coupling constant, and the quark masses. And the result agrees with the measured value to within a few percent. These calculations directly demonstrate that chiral symmetry breaking is the origin of hadronic mass. They show that if you could somehow turn off the QCD vacuum condensate while keeping everything else the same, the proton would weigh only about 10 megaelectronvolts instead of 938. The condensate is the source of almost all the mass we experience in daily life. The approximate Goldstone bosons of this symmetry breaking are the pions. In a hypothetical world of perfectly massless quarks, the pions would be exactly massless, true Goldstone bosons, as predicted by Nambu's theorem and Goldstone's theorem. In reality, because the up and down quarks have small but non-zero masses from the Higgs mechanism that explicitly break the chiral symmetry by a small amount. The pions are not massless, but merely very light, about 140 megaelectronvolts, roughly 7 times lighter than a proton, and the lightest of all strongly interacting particles. Their anomalous lightness is one of the most convincing experimental signatures that chiral symmetry breaking is real, and it is confirmed to high precision by lattice QCD calculations that can vary the quark masses continuously and watch the pion mass change exactly as predicted by chiral perturbation theory. The strange quark, heavier than the up and down quarks at about 95 megaelectronvolts, is light enough to participate partially in chiral symmetry breaking, extending the approximate symmetry from the 2 lightest quarks to 3. This gives rise to an octet of pseudo-Goldstone bosons, the 3 pions, the 4 kaons, and the eta meson. The heavier quarks, charm, bottom, and top, are too massive for chiral symmetry to be relevant to their physics. The top quark, in fact, is so heavy that it decays before it can even form a bound state, making it the only quark that physicists can study as a quasi-free particle. So your mass, the mass you register when you step on a scale, has a dual origin. A small fraction, about 1% for the protons and neutrons in your body, comes from the Higgs mechanism, the electroweak symmetry breaking that gave fundamental particles their bare masses. The overwhelming majority comes from chiral symmetry breaking in QCD. A second, independent act of symmetry breaking driven by the non-perturbative dynamics of the strong force. You are made of broken symmetry twice over, but these are not the only symmetries the universe has broken. There is another, subtler, and in some ways more disturbing form of symmetry breaking that does not generate mass, but instead determines whether matter or antimatter prevails, and the story of its discovery is a story of shattered expectations, celebrated experiments, and a mystery that remains unsolved. For decades, physicists believed that the laws of nature treated matter and antimatter with perfect equality. This belief was codified in a set of discrete symmetries. The physical intuition ran deep. Physicists believed in symmetry the way architects believe in load-bearing walls. It was structural. It was foundational. They were certain, inviolable. If you could somehow transform every particle in the universe into its antiparticle and reflect every spatial coordinate, creating a kind of antimatter mirror world, the laws of physics should be identical. This combined symmetry was called CP symmetry, the C for charge conjugation and the P for parity. But before CP symmetry could fall, parity itself had to fall first, and the story of that fall is one of the most dramatic episodes in 20th century physics. Parity, or mirror symmetry, is the idea that the laws of physics look the same when viewed in a mirror. If you watch a physical process and then watch its mirror image, both should obey the same laws. For the electromagnetic force, this is true. For gravity, it is true. For the strong nuclear force, it is true. These forces do not distinguish between the original and its reflection. But in the mid-1950s, a puzzle arose that would shatter this confidence. Two subatomic particles, called the tau and the theta, appeared to be identical in mass and lifetime, but decayed into different numbers of pions, which meant they had different intrinsic parities. This was impossible if parity were conserved, because a single particle cannot have two different parities. Either the tau and the theta were different particles that happened to have identical masses and lifetimes, which seemed like an absurd coincidence, or they were the same particle, and parity was not conserved. This conundrum was known as the tau-theta puzzle, and it nagged at the theoretical physics community like a splinter that could not be removed. In 1956, two theoretical physicists working at Columbia University and the Institute for Advanced Study, Tsung-Dao Lee and Chen-Ning Yang, made a startling observation. While studying this puzzle, they reviewed the entire experimental literature on discrete symmetries and discovered that there was no evidence whatsoever that parity was conserved in weak interactions. The strong force and electromagnetism had been tested extensively, and parity was held in both cases. But for the weak force, the force responsible for radioactive beta decay, the question had simply never been properly asked. Nobody had performed a definitive experiment. The assumption of parity conservation in the weak interaction was just that, an assumption inherited from the other forces and never independently verified. This was an extraordinary realization. One of the most fundamental symmetries in physics had been assumed, not proven, for an entire class of interactions. Lee and Yang did not didn't merely point this out. They proposed specific experiments that could settle the question definitively. They approached Qin Wu, an experimentalist who had been born in Liu, a small town near Shanghai, in 1912, and had become one of the world's foremost experts on beta decay spectroscopy. Wu had come to the United States in 1936, originally intending to study at the University of Michigan. But after discovering that women were not permitted to use the student union there, she transferred to the University of California at Berkeley, where she completed her doctorate under the supervision of Ernest Lawrence. By the 1950s, she was at Columbia University and had built a reputation for extraordinary experimental precision. Her colleagues regarded her as one of the finest experimentalists of her generation. Wu was a meticulous and determined scientist. She had been planning a trip to the Far East with her husband, Luke Yuan, a trip they had been anticipating for some time. But after hearing Li and Yang's proposal, she canceled the trip and threw herself into the experiment with single-minded intensity. Her husband sailed for Asia alone. Wu enlisted the help of the low-temperature group at the National Bureau of Standards in Washington, led by Ernest Ambler. Because the experiment required cooling a sample of radioactive cobalt-60 to temperatures close to absolute zero, about 0.003 of a degree above 0 Kelvin. At such extreme temperatures, the thermal motion of atoms is nearly eliminated, allowing the nuclear spins to be aligned in a uniform direction by an external magnetic field. The logic was elegant. Cobalt-60 nuclei have a nuclear spin, and when cooled to millikelvin temperatures in a strong magnetic field, their spins align uniformly. Cobalt-60 undergoes beta decay, emitting an electron and an antineutrino as it transforms into nickel-60. If parity is conserved, the electrons should be emitted symmetrically in both directions along the spin axis. There should be no preference for emission toward the North Pole versus the South Pole of the aligned nuclei. A mirror image of the experiment should be indistinguishable from the original. In January 1957, Wu's team announced their result. It was devastating to the old framework. The electrons were emitted preferentially in one direction, opposite to the nuclear spin. The asymmetry was large, unmistakable, and reproducible. Parity was violated, and violated maximally. In the weak interaction, the weak force is distinguished between left and right. Nature, at the most fundamental level, had a handedness. The reaction in the physics community was one of shock. Wolfgang Pauli, upon hearing the news, reportedly exclaimed that it was total nonsense when assured the results were solid. He demanded the experiment be repeated. Richard Feynman, who had bet $50 against parity violation, quietly paid up. Li and Yang received the Nobel Prize in Physics later that same year, 1957, one of the fastest awards in Nobel history. whose experimental brilliance made the discovery possible, was not included in the prize. This exclusion has been widely regarded as one of the great injustices in Nobel history. Physicists quickly recovered from the shock by proposing that the true symmetry of nature was not parity alone or charge conjugation alone, both of which were now known to be violated by the weak force, but the combination CP, if you simultaneously replaced all particles with their antiparticles and reflected the spatial coordinates, the laws of physics should be unchanged. For a few years, CP symmetry was accepted as the new sacred principle. Then, in 1964, an experiment at Brookhaven National Laboratory on Long Island obliterated that hope as well. James Cronin and Val Fitch, along with their collaborators James Christensen and René Turle, were studying the decays of neutral kaons. Their experiment was not designed to revolutionize physics. It was primarily intended to study a phenomenon called regeneration, and the CP violation search was listed as a secondary objective. The experiment sent a beam of neutral kaons down a 17-meter beamline, long enough that only the long-lived component should survive. At the end, a pair of spectrometers measured the decay products. If CP symmetry were exact, the long-lived kaon could only decay into 3 pions, never 2. But Cronin and Fitch found 45 events, plus or minus 9, in which the long-lived kaon had decayed into exactly 2 pions. The branching ratio was about 2 parts in 1,000. It was small, but it was real, statistically significant, and reproducible. CP symmetry was violated. The discovery was met with disbelief, then reluctant acceptance, then a flood of theoretical activity. The effect was tiny, a fraction of a percent, but its implications were enormous. It meant that the laws of physics treated matter and antimatter differently, not by much, but differently. The universe, at the most fundamental level, has a preference. It is not a strong preference. It is not an obvious preference, but it is real, and it is consequential. Cronin and Fitch received the 1980 Nobel Prize for their discovery. But explaining why CP symmetry was violated took nearly another decade. In 1973, Makoto Kobayashi and Toshihide Masukawa, 2 Japanese physicists working at Nagoya University, proposed a framework that would eventually solve the puzzle. Their idea was elegant and audacious. They showed that CP violation could be naturally accommodated within the standard model, but only if there existed at least 3 generations of quarks. At the time, only 3 quarks were known: up, down, and strange. Kobayashi and Masukawa predicted that 3 more must exist: charm, bottom, and top. The mathematical reason is subtle but beautiful. The mixing between quark flavors in weak interactions is described by a matrix, now called the CKM matrix, after Nicola Cabibbo, who first proposed the mixing, and Kobayashi and Masukawa, who extended it with only 2 generations of quarks. This matrix is a simple 2x2 rotation, and it contains no room for a complex phase. Without a complex phase, CP violation cannot occur, but with 3 generations, the matrix becomes a 3x3 object, and it necessarily contains one irreducible complex phase. This single phase is the source of all CP violation in the quark sector of the Standard Model. It is a number, and its value has been measured with increasing precision over the decades. The charm quark was discovered in 1974, the bottom quark in 1977, and the top quark in 1995, vindicating the Kobayashi-Maskawa prediction. Their framework was further confirmed in the early 2000s by the Babar experiment at Stanford and the Bell experiment in Japan, which observed large CP violation in the decays of B mesons, exactly as the CKM framework predicted. These B factory experiments measured the angles of a geometric construction called the unitarity triangle, and the results were spectacularly consistent with the Kobayashi-Maskawa theory. For this work, Kobayashi and Maskawa shared the 2008 Nobel Prize with Nambu. Since then, CP violation has been observed in multiple particle systems. In 2019, the LHCb experiment at CERN detected CP violation in the decays of charm mesons, the first observation in particles containing charm quarks. And in 2025, the LHCb collaboration extended this story further by observing CP violation for the first time in the decay of baryons, the 3 quark particles that include protons and neutrons. The observed asymmetry between baryon and antibaryon decay rates was about 2.5%, consistent with theoretical predictions. This was a particularly significant milestone because baryons, not mesons, are the particles that constitute all the visible matter in the universe. The protons and neutrons in your body are baryons, and the fact that CP violation occurs in their decays connects the abstract mathematics of the CKM matrix directly to the question of why you exist. And this brings us to the deepest question of all. Why is there something rather than nothing? In 1967, the Soviet physicist Andrei Sakharov, who would later become famous as a dissident and human rights advocate, identified 3 conditions that must be satisfied for a universe that starts with equal amounts of matter and antimatter to evolve into one dominated by matter. First, there must exist interactions that violate baryon number conservation, processes that can change the total number of baryons. Second, there must be violations of both C-symmetry and CP symmetry, so that reactions producing matter can proceed at a different rate than reactions producing antimatter. Third, these processes must occur out of thermal equilibrium, because in equilibrium, every reaction is balanced by its reverse, and no net asymmetry can accumulate. These are called the Sakharov conditions, and they are widely considered the necessary prerequisites for baryogenesis, the production of the observed excess of matter over antimatter. Each condition addresses a specific requirement without baryon number violation. You cannot change the total count of baryons, so you could never go from 0 net baryons to a universe full of them without C and CP violation. Any process that creates an extra baryon would be exactly balanced by a process that creates an extra antibaryon, and the net effect would be 0 without departure from thermal equilibrium. The principle of detailed balance ensures that every forward reaction is matched by its reverse, again producing 0 net change. The Big Bang satisfies the third condition naturally through its rapid expansion and cooling, driving the universe relentlessly away from equilibrium. The Standard Model contains exotic processes called sphalerons that violate baryon number conservation at extremely high temperatures, above about 10 tera-electronvolts. Sphalerons are not ordinary particle reactions. They are non-perturbative processes, meaning they cannot be described by the usual Feynman diagram approach. Instead, they involve collective transitions of the gauge fields over energy barriers, converting baryons into leptons, and vice versa, at the temperatures prevailing in the electroweak epoch. Sphalerons were rapid and common. They could have reshuffled the baryon number of the universe on timescales much shorter than the expansion rate and CP violation discovered by Cronin and Fitch and explained by Kobayashi and Maskawa, provides the asymmetry between matter and antimatter reactions. But there is a devastating problem: the amount of CP violation contained in the Standard Model, quantified by the parameters of the CKM mixing matrix, is far too small. Detailed calculations show that the known sources of CP violation produce a matter-antimatter asymmetry many orders of magnitude below what is needed to explain the observed ratio of roughly 1 baryon for every billion photons in the cosmic microwave background. The Standard Model gets the qualitative picture right. Matter and antimatter behave differently, but quantitatively, it falls short by a factor that is difficult to even express in ordinary language. This is one of the greatest unsolved problems in all of physics. Something beyond the Standard Model must have contributed additional sources of CP violation in the early universe, tipping the balance just enough to leave behind the 1 in a billion residue of matter from which all the stars, galaxies, planets, and organisms in the observable universe were eventually built. The magnitude of the problem is staggering. We can measure the baryon to photon ratio in the universe today by studying the cosmic microwave background radiation and the abundances of light elements produced during Big Bang nucleosynthesis. The number is approximately 6 times 10 to the negative 10. For every photon in the universe, there are about 6 10-billionths of a baryon. That is the leftover. Everything else, all the antimatter that was created alongside the matter annihilated. The photons we see in the cosmic microwave background are, in large part, the ash of that annihilation, and the Standard Model, with all its known CP violation, produces a baryon asymmetry that is roughly 10 orders of magnitude too small to explain this number. The gap between prediction and observation is not a factor of 2 or 10. It is a factor of billions. This tells us something profound. The Standard Model, despite its extraordinary success in describing particle physics at energies accessible in laboratories, is incomplete. There must be new physics at work, new particles, new interactions, or new symmetries and new symmetry breakings that we have not yet discovered. The baryon asymmetry of the universe is one of the strongest pieces of evidence that the Standard Model is not the final theory. Physicists are actively searching for this additional source of CP violation through multiple experimental avenues. Experiments studying neutrino oscillations, such as the Deep Underground Neutrino experiment being built in the United States and the Hyperkamiokande detector in Japan, are designed to measure CP violation in the lepton sector. Neutrinos oscillate between 3 flavors: electron, muon, and tau, as they travel through space, and the pattern of these oscillations is governed by a mixing matrix analogous to the CKM matrix for quarks. This leptonic mixing matrix, called the PMNS matrix, may contain a CP violating phase. If neutrinos and antineutrinos oscillate at different rates, it would be direct evidence of leptonic CP violation, which could power a mechanism called leptogenesis. In leptogenesis, a lepton asymmetry generated in the very early universe, potentially through the decay of extremely heavy right-handed neutrinos, is converted into a baryon asymmetry through Sphaleron processes. This is currently one of the leading theoretical candidates for explaining the matter-antimatter asymmetry. Other experiments are pursuing different clues. Searches for the electric dipole moment of the neutron, conducted at facilities around the world, probe CP violation with extraordinary sensitivity. A permanent electric dipole moment of the neutron would be a direct signal of CP violation beyond the Standard Model. So far, measurements have found it to be consistent with 0, placing increasingly stringent constraints on new physics. But the searches continue, because even a tiny, non-zero value would revolutionize our understanding. The electroweak phase transition itself may hold the key in some extensions of the Standard Model. With additional Higgs fields or new particles, the transition from the symmetric to the broken symmetry phase could be a violent first-order phase transition, rather than the smooth crossover predicted by the Standard Model alone. In a first-order transition, bubbles of the new broken symmetry phase would nucleate within the old symmetric phase and expand outward, much like bubbles of steam forming in boiling water. The conditions at the expanding bubble walls, where the Higgs field is changing rapidly, and the system is far from equilibrium, could provide exactly the right environment for generating a baryon asymmetry, with CP-violating interactions processing matter and antimatter differently as they pass through the wall. In the Standard Model alone, with a Higgs boson of 125 gigaelectronvolts, the transition is a smooth crossover, too gentle to produce the required out-of-equilibrium conditions, but extensions involving additional scalar fields, supersymmetric partners, or other new particles could make the transition first-order and violent enough to work. Gravitational wave detectors like LISA, planned for launch in the 2030s, may even be able to detect the echoes of such a transition, preserved as a stochastic background of gravitational waves generated by colliding bubbles in the early universe. Every atom in your body, every bit of matter on Earth, and in every star you can see, is the leftover from this process. For every billion pairs of quarks and antiquarks that annihilated into radiation in the first seconds after the Big Bang, one quark survived. Those survivors formed protons and neutrons, which combined into atomic nuclei during the first few minutes, which captured electrons hundreds of thousands of years later to form neutral atoms, which over hundreds of millions of years collapsed under gravity into stars and galaxies and planets, and ultimately into you. You are the residue of an imperfection, a cosmic rounding error, a 1 in a billion leftover from the most comprehensive annihilation in the history of the universe. And the specific imperfection that saved you remains one of the deepest mysteries in all of science. Somewhere in some corner of physics we have not yet explored, there's a source of CP violation large enough to explain why you are here. Finding it is one of the central goals of 21st century particle physics, and it may require entirely new kinds of experiments, new accelerators, new detectors, and perhaps entirely new theoretical frameworks that we have not yet imagined. There is one more unsettling dimension to this story, and it concerns the possibility that the symmetry breaking which gave rise to mass and matter may not be the final word. The Higgs field settled into a particular value, about 246 gigaelectronvolts, in the valley of the Mexican Hat potential. But what if that valley is not the deepest one? What if there is a lower energy state, a deeper trough, separated from our current vacuum by an energy barrier? When physicists measured the mass of the Higgs boson and combined it with the measured mass of the top quark, they could calculate the shape of the Higgs potential at extremely high energies using a technique called renormalization group evolution. This technique traces how the coupling constants of the Standard Model change as you probe the theory at higher and higher energy scales. The result was startling, and to some physicists, deeply unsettling. At energy scales above roughly 10 to the 11th gigaelectronvolts, the Higgs self-coupling, the parameter lambda that determines the curvature of the Mexican Hat potential, appears to turn negative. This means the potential develops a second minimum, far from the current vacuum state. A minimum that is actually lower in energy than the one we currently occupy. If this calculation is correct, then our current vacuum is not a true vacuum. It is a false vacuum, a metastable state balanced on a shelf above a deeper, more stable valley. The universe has been sitting in this state for 13.8 billion years, but it need not sit there forever. Through the quantum mechanical process of tunneling, a small region of space could spontaneously transition from the false vacuum to the true vacuum, much as a marble balanced in a shallow bowl might suddenly quantum tunnel through the wall of the bowl into a deeper basin outside. If that happened, a bubble of true vacuum would form and begin expanding at the speed of light. Inside the bubble, the laws of physics would be fundamentally different. The masses of particles would change. The strengths of forces would be altered. Atoms, as we know them, could not exist. Chemistry would be impossible. Life would be impossible. The bubble would be an expanding sphere of total transformation, rewriting the physical laws of every region it engulfs. And because it travels at the speed of light, no warning signal could ever outrun it. One moment, everything is normal. The next one arrives. As the physicist Sidney Coleman once wrote, vacuum decay is the ultimate ecological catastrophe. In the new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, but so is chemistry as we know it. The probability of this event is extraordinarily low. Calculations consistently show that the expected timescale for spontaneous vacuum decay is vastly longer than the current age of the universe, perhaps 10 to the power of hundreds of years or more. The universe would have to wait an almost unimaginable amount of time before such a tunneling event became likely anywhere in the observable cosmos. But the probability is not zero, and physicists take it seriously because the early universe provided conditions far more extreme than anything we experience today. During cosmic inflation, the rapid exponential expansion of space generated enormous energy densities and quantum fluctuations of all fields, including the Higgs field. If the Higgs potential truly has a deeper minimum at high field values, then during inflation, the Higgs field could have been kicked to large values by these fluctuations, potentially triggering a catastrophic transition to the true vacuum. The period immediately after inflation, called reheating, was equally dangerous, as the energy driving inflation converted into particles and radiation. Certain quantum modes could have been amplified in a violent burst called preheating, generating fluctuations large enough to push the Higgs field over the barrier. The fact that none of this happened, that the universe survived both inflation and reheating without decaying to the true vacuum, is itself a piece of physical evidence. It constrains the scale of inflation, the dynamics of reheating, and the possible couplings of the Higgs field to other fields and to space-time curvature, some researchers have shown that a non-minimal coupling of the Higgs field to gravity, a term in the equations that links the Higgs field's value to the curvature of space-time, could stabilize the false vacuum during inflation, even if the standard model parameters alone would predict decay. This is a striking example of how cosmology and particle physics constrain each other. The survival of our vacuum tells us something about the laws of physics at energy scales we cannot directly probe in any laboratory. In 2015, researchers pointed out that primordial black holes, if they exist, could serve as nucleation seeds for vacuum decay, potentially vastly increasing the decay rate in their vicinity. However, the authors noted that if primordial black holes had triggered a vacuum collapse, it should have happened long before the emergence of life on Earth, since primordial black holes would have existed since the very early universe. A subsequent study in 2017 suggested that the resulting bubble would collapse into a black hole rather than expanding to destroy the universe, offering a potential safety mechanism. In 2019, another study found that rapidly spinning black holes could actually stabilize the false vacuum, reducing decay rates below the flat spacetime prediction. Some physicists find the metastability of the Higgs vacuum deeply troubling. Others find it fascinating. A universe balanced on a knife edge, existing in a state that is not its deepest possible energy, has a certain poetic resonance. It suggests that the current configuration of reality, the specific pattern of symmetry breaking that gives us mass and matter and chemistry and life, might not be permanent. It is stable enough to have lasted for nearly 14 billion years, but it may not last forever. We might be living in a universe that is, in a very precise mathematical sense, provisional. It is worth emphasizing that these calculations depend sensitively on the precise values of the Higgs boson mass, the top quark mass, and the strong coupling constant, all of which have experimental uncertainties. Small shifts in these measured values could move the vacuum from metastable to absolutely stable, or from metastable to outright unstable. Future measurements at upgraded colliders and next-generation experiments may resolve this question definitively. If the vacuum is truly metastable, it would be one of the most profound revelations in the history of science, a discovery that even the ground state of reality is provisional. And so we arrive at the end of this story, except that it is not really an end. It is a frontier. The standard model of particle physics is the most successful scientific theory ever constructed. It accounts for the behavior of all known fundamental particles and 3 of the 4 fundamental forces with a precision that has been verified to as many as 10 decimal places in some experiments. At its heart are symmetries, mathematical structures that dictate the existence and properties of every particle and interaction. And at its heart, equally, are the breakings of those symmetries, the imperfections and instabilities that transform a symmetric, featureless void into a universe teeming with structure and complexity. Electroweak symmetry breaking, driven by the Higgs field settling into a non-zero vacuum value roughly a trillionth of a second after the Big Bang, gave fundamental particles their bare masses and separated the electromagnetic and weak forces into the distinct phenomena we observe today. Chiral symmetry breaking in quantum chromodynamics generated more than 99% of the mass of ordinary matter, converting the almost weightless quarks and gluons into the substantial protons and neutrons that form the nuclei of atoms. CP violation, the breaking of the symmetry between matter and antimatter, ensured that not all matter annihilated in the first seconds of cosmic history, leaving behind the 1 in a billion residue from which the entire observable universe is built. Each of these breakings was imperfect in a specific and essential way. The Higgs mechanism left the photon massless while giving mass to the W and Z bosons, creating the vast difference in range between electromagnetism and the weak force. Chiral symmetry breaking left the pions anomalously light, the ghost of the Goldstone theorem, while generating the bulk of the mass of everything we can touch. CP violation was tiny, less than 1% in most measured systems, but precisely large enough to tip the cosmic balance. If any of these breakings had been perfect, if the symmetry had been preserved or broken with exact mathematical precision, the universe would be radically different. In most of those alternative scenarios, it would be empty, yet the standard model cannot be the final word. It does not explain why the Higgs field has the particular potential it does. It does not explain why the vacuum expectation value is 246 gigaelectronvolts and not some other value. It does not account for the observed pattern of fermion masses, why the electron is hundreds of thousands of times lighter than the top quark, or why there are 3 generations of matter particles and not 2 or 4 or 17. It does not contain enough CP violation to explain the dominance of matter over antimatter. It does not incorporate gravity, and it says nothing about dark matter or dark energy, which together constitute roughly 95% of the energy content of the observable universe. An omission so vast it borders on the embarrassing for a theory we call the standard model. These are not minor loose ends. There are gaping holes in our understanding, and they almost certainly point to deeper layers of symmetry and deeper layers of symmetry breaking that we have not yet uncovered. The history of physics suggests that every time we have understood a symmetry, we have found it to be part of a larger one. Maxwell unified electricity and magnetism, revealing the electromagnetic symmetry. Glashow, Weinberg, and Salem unified electromagnetism and the weak force, revealing the electroweak symmetry. Each unification revealed a more symmetric theory that was broken at the energy scales we can observe, producing the apparently distinct phenomena we experience, the symmetries that the standard model is built upon may themselves be fragments of a larger, more unified symmetry group, one that was whole in the earliest moments of the universe and broke apart in stages as the cosmos cooled. Grand unified theories attempt to unify the strong, weak, and electromagnetic forces into a single gauge group, perhaps SU5 or so 10, that fractures through successive symmetry breakings at progressively lower energies, at energies around 10 to the 15th or 10 to the 16th gigaelectronvolts, far above anything accessible in current or foreseeable particle colliders. These theories predict that the three forces were indistinguishable, governed by a single coupling constant. As the universe cooled below this scale, the grand unified symmetry broke, separating the strong force from the electroweak force. Then, at a much lower energy scale, the electroweak symmetry itself broke, separating electromagnetism from the weak force. Each breaking produced a more complex, more differentiated universe from a simpler, more symmetric precursor. Supersymmetry proposes yet another layer of broken symmetry, a symmetry between fermions and bosons, the two fundamental categories of particles in a supersymmetric world. Every known particle would have a partner of the opposite statistical type. Every fermion would have a bosonic superpartner, and every boson would have a fermionic superpartner. Supersymmetry, if it exists, must be broken at energies above what current experiments can reach, because no superpartners have been observed at the LHC. But the breaking of supersymmetry could solve multiple outstanding problems simultaneously. It could stabilize the Higgs mass against enormous quantum corrections. It could provide a candidate for dark matter in the form of the lightest superpartner. And it could bring the 3-gauge coupling constants closer to unification at high energies. Whether any of these grander frameworks will prove correct remains to be seen. The next generation of experiments may provide answers. The high luminosity upgrade of the LHC, scheduled to begin operations in the late 2020s, will deliver 10 times more collision data, enabling precision measurements of the Higgs boson's properties, including its self-coupling, that could reveal deviations from standard model predictions. Next-generation neutrino experiments will search for CP violation in the lepton sector. Gravitational wave observatories in space may detect the signatures of first-order phase transitions in the early universe and proposed future colliders, including circular electron-positron colliders and muon colliders, could probe energy scales far beyond the LHC's reach, potentially discovering new particles and new symmetries that the current generation of experiments has only hinted at. But the central insight is already established beyond any reasonable doubt. The universe is not made of symmetry. It is made of symmetry's ruins. The laws are symmetric. The world is not. And from that gap, from that essential tension between the elegance of the equations and the messiness of the outcomes arises everything that exists. Every atom in your body, every star in the sky, every thought you have ever had, all of it is the consequence of perfection failing to maintain itself, of the universe choosing imperfection over sterility, complexity over emptiness, existence over the void. There is a deep philosophical resonance to this idea. The universe had every opportunity to remain simple. It could have stayed symmetric, pristine, and dead. Instead, something fell. A field tipped off a peak. A vacuum chose a direction. A condensate formed. A symmetry cracked, and from each crack, from each imperfection, emerged a new level of structure, a new kind of richness, a new possibility for the emergence of beings who could look back at the process and wonder how it all began. Nambu, the quiet genius who started it all, put it best in his Nobel lecture. "The basic laws are very simple," he said, "yet this world is not boring." That is, I think, an ideal combination. You are the proof that he was right. Thanks so much for watching. If you enjoyed this, go ahead and hit that like button, subscribe to the channel, and leave a comment below telling us what you think about the idea that everything in the universe owes its existence to broken symmetry. We read every comment. Thanks for watching, and we will see you next time.